Annette, Anthony, Ayla, Kevin. Great, great, great. All right, so this is my class sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate. Please do not share any social media or contact info for your own security reasons. So again, we're going to actually do a second review day. Again, the exam will actually be tomorrow. Tomorrow we don't have live sessions, so I'll just have that recording up there for you that goes over every question. Again, no straight answers, but it does go over all the background information to help you be successful and to kind of review everything that we've learned throughout the unit, since I know Unit 3 especially was a while ago. All right, so let's go ahead and do some review today. So remember we talked about the mole. Much like the word dozen, the word mole in chemistry also stands for a certain amount. So while dozen means 12, mole means 602 times, or sorry, 6.02 times 10 to the 23rd. So this big, big number. Particularly, we usually use it in terms of this number of atoms, molecules, or particles. But you could say that you have a mole of money, which would be a lot of money, and I wish we all at some point have a mole of money. Hi, Sylvia. Good to see you. How are you? So again, an easier way to write this is 6.02 times 10 to the 23rd, particles per mole, atoms per mole, molecules per mole, et cetera, et cetera. This is also called Avogadro's number. Remember that when you do plug this into a calculator, because you will need to be able to use this number tomorrow, the calculator has a couple different options. You can use the EXP button. You don't have to say times 10 to, just instead of saying times 10 to, you put EXP, so 6.02, EXP3, 23, or you can also use the capital E, but do not use the lowercase e. The lowercase e is a totally different thing. All right, everybody in the chat box, give me a music note if that makes sense. All right, we just reviewed what a mole is, and we're going to go ahead and apply it in just a moment. Excellent. I see Annette, I see Christine, Sylvia. Music notes, thank you. If we remember this review about the mole, remember this right here is kind of our magic number, Avogadro's number. Thank you, Ayla. Excellent. All right, let's go ahead and actually begin to practice this. So go ahead, tell me in the chat box again, what is the molar mass of sulfur? Take a look at our periodic table box for sulfur and tell me which of these tells us mass. Is it the top number or the bottom number? Which one tells us the molar mass, the mass of sulfur? You have a 50-50 chance, so tell me which of these two numbers tells me mass. Remember, we learned what the top number means, we learned what the bottom number means. Which of those means mass? Excellent. I see Christine, I see Sylvia. Great. I see Ayla working, Annette working, Natalie working. Get your answers in there. Make sure you're participating. Again, if I don't see participation over several slides, I'll go ahead and check in with you in the check-in room. Thank you, Kevin. Yes, perfect. Anne-Marie, yes. It's going to be this bottom number. You're absolutely right. So molar mass comes from this bottom number. And remember, that would be 32.06. And the units would be grams per mole. Grams per mole. Now, taking a look there, if we have 1 mole of this, so if we did in fact have 32.06 grams, that means we have 1 mole, then how many atoms would that be? All right, if we had 32.06 grams or 1 mole, how many atoms would that be? Again, that's our magic number. How many atoms are in our magic number? Okay, one more time. Let's go back to this slide and just type this in the chat box. What is the magic number? What is the magic number? All right, get used to practicing this. The answers on the board tell me how many particles are in 1 mole. No matter what that weight of the mole is, there's always this many particles. So what is that number? I need everyone typing it in the chat box. I need everyone getting used to practicing typing this. Hi, Ken. Good to see you. How are you? Awesome. I see Annette typing. I see Ayla typing. I see Natalie typing. Again, how many particles are in 1 mole? The answer's on the board. I'm literally pointing to it. It's literally boxed. Please type that in the chat box so that I know that you are practicing typing it. Great. I see Annette. I see Natalie. I see Ayla. Exactly, exactly. Looking good. Thank you. Thank you. Get your answers in there. I see Gabby working, Anthony working. Again, you will need to know this number for tomorrow's exam. So I need you practicing right now. That way you are ready for tomorrow's exam. Thank you, Anthony. I see Gabby, Kevin working. Again, the answer's on the board. I'm pointing to it. I need you to type it in the chat box. Thank you. I see Ryan working. I see Amy working. Ken working. Thank you. Looking good, everybody. Awesome. All right, so it looks like most of us have got it. You are correct. In 1 mole of sulfur, there's always going to be 6.02 times 10 to the 23rd atoms. 6.02 times 10 to the 23rd atoms. That's just our magic number. That is Avogadro's number. As long as we know there's 1 mole, doesn't matter if that 1 mole weighs 32 grams, if it weighs 100 grams, if it weighs 1,000 grams. If there's 1 mole, we know no matter what, that means 6.02 times 10 to the 23rd atoms or particles of that substance. Let's go ahead and practice one more time. What is the molar mass of calcium? All right, we identified the molar mass of sulfur. Let's go ahead and try calcium now. What is the molar mass of calcium? Everybody should be able to do this. We just did an example together, and the example is still on the board. So it should be pretty easy to take a look at our original example and do it again. Thank you, Christine. Thank you, Annette, Sylvia, Natalie, Anne-Marie. Beautiful. Yes, molar mass of calcium. We take a look at that bottom number. Bottom number tells us mass. And so you are totally correct. This would be 40.078 grams per mole. Beautiful. And if we had 1 mole, which in this case weighs 40.078 grams, all right, but it's still 1 mole. If we have 1 mole, then no matter what, 1 mole always means how many atoms? 1 mole always means how many atoms? I see Christine in the chat box. I see Annette typing. Again, we already did this one up here. We should be able to do the same thing down here. In 1 mole. 1 mole always means what? Again, doesn't matter how much it weighs. It could weigh 32 grams. It could weigh 40 grams. It could weigh a bajillion grams. If you have 1 mole of something, it always means what? Just like you could have a dozen elephants or a dozen rabbits, a dozen always means 12. In the same way, 1 mole always means, thank you, Natalie, thank you, Annette, thank you, Christine, thank you, Anne-Marie. Yes, you are correct. It always means 6.02 times 10 to the 23rd atoms. Great job. How are we feeling about this? Go ahead and give me a lightning bolt if you remember this, if this review helps you. Go ahead, lightning bolt if that makes sense. Thank you, Annette. Thank you, Ayla. Thank you, Amy. Natalie, Anthony, Anne-Marie. Beautiful, Sylvia. All right, awesome. Let's go ahead and review this. Now, remember, chemical reactions occur anytime that bonds are rearranged. So that means that elements could bond together. So for example, you can see that this element A is bonding with element B over here. This could also mean that bonds are being broken, right? So you can see this compound made up of A and B is breaking down into separate pieces, A plus B. Or in general, it can mean that bonds are being rearranged. So these two examples are examples of rearranging. The chemicals are coming back together in a different form. Now, when chemical changes happen, remember that heat either gets absorbed or released. Remember, when we say heat gets absorbed, is that endothermic or exothermic? Remember, absorbed means it's going, heat is entering. So is that going to be endothermic or exothermic? Go ahead and tell me in the chat box. If heat is entering, is that endothermic or exothermic? Thank you. I see Christine. I see Sylvia, Anne-Marie, Amy, Annette, Ayla. Beautiful. Yes, this means it's going to be an endothermic reaction. And therefore, if heat is being released and heat is exiting, then that would be what? Heat exiting is what? Again, even if someone else has the same answer, you should still type it because I want you to get used to writing these answers. You will need to be able to do this in tomorrow's exam. So make sure you are practicing for yourself. No one else can learn for you. Yeah, this is going to be exothermic, an exothermic reaction. So again, one of the main characteristic of a chemical reaction is bonds have to be rearranged. You have to start off with one type of chemical and it needs to change to different chemicals. Now this brings us to chemical reactions result in chemical changes. So chemical changes means that different substances are being formed, like rust takes iron and oxygen and creates a totally different substance, rust, which is iron oxide. Fire takes a material and oxygen and then creates water and carbon dioxide and heat, totally different substances. Same thing, pennies being tarnished by oxygen takes copper, and that copper is then changed into a different chemical. So anytime we have chemical changes, that means there's a chemical reaction. That means different substances are being formed. This is different than physical changes. We talked about how phase changes, so freezing and melting and evaporation or vaporization and condensation, all of those things are only physical changes because those things are chemically still the same. For example, in the chat box, ice, water, and steam are all still chemically what? What is the chemical formula regardless of if you're ice, water, or steam? What is the chemical formula of the molecules in all of these examples? Chemical formula of ice, water, and steam. Give me the letters, give me the numbers. Water is what? Thank you. I see Ryan on top of it, nice and fast. I see Annette working. Yes, exactly. Ice is going to be made up of H2O. Water is going to be made up of H2O, and steam is still made up of H2O. So no matter what, these are not changing chemically, right? So these are only physical changes. Again, what you start with has to be different from what you end with. Our example in class was we mixed baking soda and vinegar. They reacted to form bubbles, which were carbon dioxide gas, water, and a salt, a sodium acetate salt, which is the salt that is used on chips, like salt and vinegar chips. Okay, let's go ahead and make sure we understand this. This is a problem that we saw in class. That's what we're doing right now. We're reviewing. Select all of the correct statements about chemical changes. All right, if we have chemical changes, what is happening? All right, box one of the blues. Bonds stay the same for the substance. Bonds are broken, formed, or rearranged. Choose one of the pinks. Different chemical substances are formed at the end, or the substances stay chemically the same from start to end, and choose one of the greens. An example is freezing carbon dioxide gas into dry ice, or an example would be baking soda and vinegar reacting to form carbon dioxide, water, and sodium acetate. Go ahead, box all of those correct statements up on the board for us, please, and thank you. Love it. I see you working hard up there. Let's see who I've got up there. I see Amy, Annette, Christine working hard. I see Ryan working hard. Awesome. Looking good. Kevin is up there. Natalie is up there. Anne Marie, awesome. Looking good, everybody. Kevin, I think your tools went a little bit crazy. All right, let's go ahead and pause those tools. Take a look here. Yes, remember, chemical changes means that things have to change. So that means bonds have to be broken, bonds have to be formed or rearranged to create totally different substances. That was the pink answer. Different substances are formed at the end. And you are correct. An example would be baking soda, vinegar, changing into carbon dioxide, water, and sodium acetate. The reason the freezing carbon dioxide gas is not a difference is because dry ice is still made up of CO2. So regular carbon dioxide gas is CO2 and dry ice is still CO2. Go ahead, everybody in the chat box, give me a coffee cup if you feel comfortable with this review. Coffee cup if you feel comfortable with this review. Thank you, Christine, Annette, Sylvia. Great job, everybody. Thank you, Ayla. Love it. All right, let's go ahead and review how to balance equations. We should feel pretty comfortable with this. We reviewed it in 4 different classes, but just in case we're reviewing it right now because you will need to be able to balance a reaction tomorrow for your exam. So in our example, we just talked about rust. Iron reacts with oxygen to form iron oxide, which is known as rust. So we're going to go ahead and use the drawing method in order to balance this equation. All right, so let's go ahead and take a look here. I'm going to kind of split this right here. And we're going to go ahead and draw our molecules. So let me grab my tools here. All right, so iron, right? I'm going to draw that as well, iron by itself is only an atom, but we'll say that it's drawn in its own circle, oxygen in its own circle, and iron oxide in its own circle. Let's take a look here. In iron, how many Fe's should I put in iron? Remember, this is reading chemical equation or chemical formulas, which we reviewed yesterday. If there's no number after this, no number means? Yep, no number means 1. So I'm going to go ahead and just draw 1 Fe in here. Good. O2, how many oxygens should I draw in this molecule of O2? Again, reading that formula correctly. Yep, we have 2 oxygens in O2. All right, I'm going to go ahead and also start our counts. So on the left, we currently have 1 iron. We currently have 2 oxygens. Now, on the right, we have Fe2O3. How many irons are in Fe2O3? How many irons are in iron oxide? Take a look at the number after the atom. Yep, good. So Fe2 is going to be 2 irons. And how many oxygens are in Fe2O3? How many oxygens are there? Again, you need to be able to do this tomorrow. That's why we're practicing together. It is to your benefit to practice with us right now. All right, looking good. Yes, we should have 3 oxygens. Awesome, Ryan. Awesome, Ayla, Amy, Christine, and Annette. So let me go ahead and draw those 3 oxygens in there. All right, so now we want to go ahead and begin to balance this. Again, we have 3 oxygens on the right. Oops, that's a plus sign and not a 3. Sorry, that's a pound sign. There we go. All right, so let's take a look here. We currently do not have the correct number of anything, right? We only have 1 iron on the left, 2 on the right. We only have 2 oxygens on the left and 3 on the right. So let's go ahead and address the irons first. If I have 1 oxygen on the left and 2 on the right, which side needs more? Which side needs more? Which side needs more iron? Yeah, the left side. So what am I going to add? Am I going to add another iron or another O2? Am I going to add another Fe or another O2? If I need more on the left, which of these two things can I add more of to get more iron? Yeah, more Fe, obviously. O2 has no Fe in it, so that would not make sense. So let's add another Fe. Perfect. All right, so now we have 2 Fe's on the left. Great, so that looks good so far. Now let's go ahead and address the oxygens. I have 2 oxygens on the left. I have 3 on the right. Which side needs more? Which side needs more? Yes, again, the left side needs more. So one more time, should I add another Fe or add another O2? Should I add another Fe or add another O2? Yes, let's add another O2. That's the only thing that contains oxygen. Remember, we can only add more of what we already have. So here's another O, another O. So now I have 4 oxygens on the left. Are we balanced? I have 4 oxygens on the left. Are we balanced? No, so that means that we still need to go ahead and do some more work. So if I have 4 oxygens on the left and 3 on the right, which side now needs more? Which side now needs more? Go ahead, tell me in the chat box. Yeah, the right side now needs more. So what do I add to get more oxygen on the right? Again, we can only add more of what we already have. So I can't just add oxygen. I need to add an entire molecule of what? An entire molecule of what? No, we can't add O2 to the right. We don't have any O2 on the right-hand side. But what do we have on the right-hand side that I can add more of? Yeah, exactly, Amy. Awesome. Yeah, we can add another Fe2O3. So we can add another iron oxide. So let me go ahead over here. Fe, Fe, O, O, O. So now on the right, it looks like I have 4 irons and I have 6 oxygens. Are we balanced? Are we balanced? No, oh my gosh, how are we not yet balanced? This is crazy. So remember that this one is kind of a harder one to balance because you have to go back and forth a couple times, but that's okay. Take a look, I have 2 irons on the left, 2 on the right, or 4 on the right, so I need more on the left. How many more do I need on the left? How many more irons do I need on the left? Everybody tell me in the chat box. Yeah, we need 2 more, so let's go ahead. I'm gonna go ahead and just copy this and paste this and put 2 more on here. Looking good. Oops, get that. Come back. There we go. So we have now 4 of these irons. And how many more? And on the left, I have 4 oxygens. On the right, I have 6 oxygens. So I need more on the left. What should I add more of? Do I add another Fe or another O2? Do I add another Fe or another O2? On the left. We need more on the left. What do I add more of? Yeah, again, we add more O2. We add more O2. So let me go ahead and copy that. Paste this. Oops, sorry. Why did that do that? Let me try and copy that again. Copy and paste. There we go. All right. So now I have 6 oxygens on the left. Are we balanced? Are we balanced? Yes, we're finally balanced. So let's count them up. Let's make our coefficients. How many irons do I have in total? How many circles of iron do I have in total? Yes, I have 4. So in front of the Fe, I'm going to put a big 4. How many molecules or circles of O2 do we have? How many molecules or circles of O2? Yes, we have 3, so I put a big 3 in front of O2. And then how many iron oxides do we have? Big circles of iron oxide. Excellent, Christine, Amy, Annette, I see you. Yes, we have 2, so let's go ahead and draw a 2 up here. All right, so our final balanced equation or recipe is that for every 4 irons plus 3 O2 molecules, you get 2 iron oxides, 2 Fe2O3s. How do we feel about this? Give me a green check if you feel comfortable with how we balance this. I need green checks from everyone. Green checks if you feel comfortable with how we balance this. If I don't hear from you, I'll go ahead and move you to the check-in room and check in with you. Green checks, green checks. If you don't feel comfortable, you can give me a red X, but I do need some response. So I need either a green check or a red X to let me know that you are comfortable with balancing. Cool. Just waiting on a response from Madison. Madison. Waiting on Kevin, Ken, Gabby, Gabby, and Anthony T. Amy, I see you're typing, so let me know what's going on. Thank you, Kevin. Awesome. Anthony, Ken, Madison. Anthony, Ken, Madison, I need your green checks, please. All right, looking good. Thank you so much, everyone. All right, I'm just going to go check in with those students for just a moment. Give me 1 second. Give me 1 second, and I will be back. Anthony, Ken, Madison. Anthony, Ken, Madison, are you there? Oh, perfect. Okay. Perfect, Madison. I'll send you back. Thank you, Ken. Perfect. Anthony, are you there? All right. Looking good, everybody. All right, let's go ahead and move on here. So based on that, right, we should have figured out here that the correctly balanced one here is, right, 4 irons plus 3 oxygens gives us 2 iron oxides. Again, that's what we solved on the previous slide. Great job, everybody. All right, so let's go ahead and take a look at this. Remember that we talked about the magic mole ratio. Sorry. All right. So yes, the magic mole ratio comes from this balanced chemical equation. So tomorrow you're going to have to make sure you balance your equation, and then you're going to also need to make sure that you can make a magic mole ratio. So the way that we make a magic mole ratio, remember, is that we take the moles of what we're looking for divided by the moles of what you're given. And there are, in this example, there are 6 different mole ratios you can possibly make. So the nice thing is that the mole ratios are really flexible for whatever you need in your equation. So for example, you could use 1 mole of N2 divided by 3 moles of F2, or if you needed to find the opposite thing, you could actually flip it. Same thing with the other 4 examples here. Again, you can flip the mole ratios back and forth. You don't always have to use the same mole ratio. You're going to use whatever magic mole ratio makes sense for your problem. Let's go ahead and take a look at an example here. Based on our iron oxide equation that we balanced, how many moles of iron would we need to produce 20 moles of iron oxide? So remember, in the first box, we always start out with what we know. Okay, and so tell me in the chat box, what number do I already know here? Taking a look at my question, think about what number do we already know? There's a number in this problem. Can you tell me what is the number in this problem? You just need to read the problem and tell me what number do you know? What number do you see here? Awesome, I see Ryan. I see Amy typing. Thank you, Amy. I need more participation. I see Anne-Marie typing. Perfect. Thank you, Christine. Yeah, exactly. We already know that we're starting out with 20 moles of iron oxide. So I'm going to start with what I know, 20 moles of iron oxide, and I'm going to make it into a fraction by putting it over the number 1. Remember, you start out with what you know, and you put it over the number 1 to put it into fraction form. In the chat box, please give me a car if that makes sense. So start off with what you know and put it over the number 1 to make it a fraction. Thank you, Amy. I see you in the chat box. Car, if you understand how I got here, we started off with what we knew, and we put it over 1 to turn it into a fraction. Thank you, Annette. Awesome. I see Sylvia. Looking good, everybody. All right, so now we need to figure out what mole ratio should we use. So right here, I'm going to go ahead and use my magic mole ratio. Right? And the way I figure out which mole ratio I do is I'm going to figure out what do I need to get rid of. So I started off with moles of iron oxide and I want to get rid of it. In the next fraction, where do I put it to get rid of it? Do I put it on the top, the numerator, or the bottom, the denominator? Right? If we want to divide this out and get rid of it, yes, we're going to put this on the bottom. Right? Moles of Fe. Moles of Fe2O3 goes on the bottom because eventually that means that these units would divide out. All right, so that means we're getting rid of these units right here. Now, what moles am I solving for? What moles am I solving for? Again, read the question and tell me what am I solving for? All right, that's going to go on top of our mole ratio. What am I solving for? What goes on top of my mole ratio? Excellent, I see Annette. Again, what are we solving for? Take a look at the start of our question. What are we solving for? Thank you, Christine. Thank you, Ryan. Yeah, we're solving for iron, specifically moles of iron. So on top, I'm going to go ahead and put moles of iron, moles of Fe. Now, remember, we get our magic mole ratio from our equation. So moles of iron, how many moles of iron are in the equation? How many moles of iron are in the equation? I'm going to put that right next to moles of iron in my magic mole ratio. Yeah, there are 4. So right here, I'm going to go ahead and put 4 moles of iron are in my magic mole ratio. What about for iron oxide? Fe2O3, how many moles of iron oxide are in Fe2O3? Take a look at the coefficient, the blue number. Thank you. I see Annette. I see Sylvia, Amy working. Let's get some more participation. Ken, Kevin, Jennifer, Gabe, Gabby. More participation, please. Kyrie and Madison. Thank you. Yeah, we see the number 2 right next to iron oxide. So that means that in our magic mole ratio goes 2 moles. 2 moles of iron oxide. Okay, let's go ahead and solve this. Remember, the way that we solve this is that when you multiply fractions, you can multiply all the numerators together, multiply all the denominators together, and then divide them. So on the top, I'm going to go ahead and do 20 times 4. So 20 times 4. And on the bottom, I'm going to go ahead and do 1 times 2. Tell me in the chat box, what do I get on top? What do I get on top here? What is 20 times 4? 20 times 4 on the top. Yes, Annette, Christine, Amy, perfect. Yes, 20 times 4 will give me 80 on the top. What is 1 times 2 on the bottom? Everybody should be able to do this. What is 1 times 2 on the bottom? That's easy mental math. Anything times 1 equals itself, so 1 times 2 should equal. Excellent. I see Christine, Annette, Amy, I see Ayla typing, Sylvia, Ryan, Natalie, make sure I get your answers, Madison, Kyrie, Kevin, Ken. Thank you. I see Jennifer typing, Gabe, Gabby. Let's get your answers in the chat box. 1 times 2 equals what? Ryan, we're just solving the bottom right here. So 1 times 2 equals what? Thank you, Jennifer. Thank you, Natalie. Thank you, Ayla. Yep, 1 times 2 equals 2. Perfect, Kyrie. All right, so now we can go ahead and do our final division. Remember that whenever we have a fraction, like 80 over 2, that's the same as saying 80 divided by 2. 80 divided by 2. So in the chat box, what is 80 divided by 2? What is my final answer here? Yes, our final answer is 40. And take a look, what units did I have left over? Right, I crossed out a bunch of units, but what units did we end up keeping? What units did we end up keeping? Go ahead, tell me in the chat box. What were we solving for? We set this up so that we solved for what? Yeah, we set this up so that we solved for moles of iron. Remember, we never actually canceled out moles of iron, and so our unit right here should be moles of iron. Moles of iron. Great job, everybody. All right, so that is how we use that mole ratio. This is an example of a one-step stoichiometry problem. This one you should definitely be able to do in your sleep. Maybe not in your sleep, but you should definitely be able to get this one done tomorrow. Go ahead and give me a rainbow if you're beginning to feel comfortable with this. Again, start with what you know, put it over 1, figure out your magic mole ratio. Whatever you're trying to get rid of goes on the bottom. Whatever you're trying to find goes on the top. Get those numbers from the chemical equation. Beautiful. Awesome, everybody. All right. Now, taking a look here, we can actually expand this. So not only can we convert from mole to mole, just like we did, but we could also include mass, and we could also include particles and convert all the way from one of these to the other. So this brings us to the mole roadmap. Again, remember that for the same chemical, so for example, in pink here, you can use Avogadro's number to convert between particles and moles, or you can use molar mass to convert between grams and moles. Okay, same thing with the blue compound here. For the blue compound, you could use molar mass to convert between mass and moles. You could use Avogadro's number to convert between particles and moles. However, the only way for you to get from one chemical to another chemical, in this case our pink one to the blue one, is going to only be the magic mole ratio, which we just reviewed. We just did this one together. Okay, looking good, everybody. So let me go ahead and take a look here. Where are we going next? All right, so in class we did this problem. All right, how many grams of hydrochloric acid, which has a molar mass of 36.46 grams per mole, do you need to produce 65 grams of lead, which has a molar mass of 278.1 grams per mole? Here's the balanced equation. We're going to go ahead and follow these steps below. Okay, so taking a look here, what number do I already know? What am I starting with? All right, What number do I already know that I have? So we do know the molar masses, but that's not actually what we actually have. Molar mass is just like a reference number. We need to know exactly how much of something we have in this problem. So taking a look here, how many grams of hydrochloric acid? So ignore the molar masses for now. Ignore the molar masses for now and tell me what number do we start with? What number do we know? Thank you. I see Annette. I see Ayla working. Awesome. Yep, let's go ahead and take a look at this. If we're ignoring the molar masses, I'm sorry, that was a little misleading. That's my bad. So if we're ignoring the molar masses for now, what number do we know? What number do we know? I know, Ryan. My bad. You got this now. What number do we know that now, though? Awesome. I see Ayla typing. Get some more answers in the chat box, please. What are we starting with? Are we starting with grams of hydrochloric acid? Do we know that? Or are we starting off with grams of lead chloride? Do we know that? Which one do we already know? Yeah, exactly. So we already know that we have 65 grams of lead chloride. This is what we know. This is what we're going to start with. Perfect, Ayla. Perfect, Sylvia. All right, so let's go ahead and start off with this. So this is what we know. We know that we have 65 grams of lead chloride, which has the equation PbCl2. All right. Now, in order to turn this into a fraction, I put it over what number? To turn this into a fraction, I put it over what number? Again, to turn something into a fraction, you just need to put it over the number what? Go ahead, tell me in the chat box. Anything can be made into a fraction by putting it over what number? Yeah, over the number 1. Perfect. So we're going to go ahead and put it over the number 1. Awesome. Now let's go ahead and move on to our next step. Next step here, okay? So remember, we are starting off with grams. So that means we're starting off with the mass of PbCl2, of lead chloride. And so the next step is to find the moles of it. Remember the way that we find the moles, it tells you right here, is to use the molar mass. Take a look up here. What is the molar mass of lead chloride? That's in parentheses. Find the molar mass of lead chloride. In the chat box, what is the molar mass of lead chloride? Please work quickly. I do want to let you out on time, but because we're taking a little bit of time to participate, we're going to have to go a little bit into passing period. So please work quickly. What is the molar mass of lead chloride? Again, it's one of these parentheses. Which one is lead chloride? Awesome. I see Sylvia. I need more participation. I see Annette typing. I see Natalie typing. Ryan typing. Yeah, exactly. It's going to be this number right here. So 278.1 grams per mole. Now remember that we can make this into a fraction. So 278.1 grams all over 1 mole, right? Per mole means over 1 mole. Or we could even flip this depending on what we need. And we could say the opposite. We could say 1 mole of lead chloride. Sorry, I should label it. All over 278.1 grams. 278.1 grams of lead chloride. Taking a look here, all right, remember that we want to get rid of units. So I have grams of lead chloride on the top here. Where does it need to go in the next box? Where does it need to go in the next box? Thank you, Annette. It needs to go on the bottom. So grams of PbCl2 needs to go on the bottom here. So which of these two fractions has grams of lead chloride on the bottom? The first fraction or the second fraction? Which one should I use? Again, I can use either one. I just need to use the correct one. So either of these can be used. You just need to identify the correct one. Yeah, we're going to go ahead and use the second one. So let me go ahead and move the second one up here. All right, and that will get rid of the grams of lead chloride. Beautiful. All right, so now we're still not there yet because remember what we're solving for is grams of hydrochloric acid. Solving for grams of hydrochloric acid, and we're currently only up to moles of of lead chloride. So let's go ahead and keep on moving. We need to go ahead and do another step. Remember our next step, so this was the molar mass. All right, our next step is to go ahead and use the magic mole ratio. So we need to get to hydrochloric acid, we're going to use the magic mole ratio. All right, so taking a look here, if I have moles of iron oxide of iron chloride on the top, obviously in the next step, it needs to go on the bottom. So moles of iron chloride, lead chloride on the bottom. Now, what goes on the top? What am I solving for? Again, what goes on the top is what you're solving for. So what are we solving for in our problem? What are we solving for in our problem? What is our blue compound? All right, we did lead chloride. That's kind of our pink compound. Now where are we going? What is the compound we're solving for? I already kind of wrote it up there on the board. So what are we solving for? Yeah, so we're trying to solve for hydrochloric acid, right? We can't quite get to grams yet. We're still only at the mole step, so I'm going to go ahead and put moles of hydrochloric acid because eventually we want to get to hydrochloric acid. Excellent. Okay, so let's go ahead and find our mole ratio. Remember the mole ratio, the magic mole ratio comes from the equation. So how many moles of HCl are in the equation? How many moles of HCl are in the equation? Yes, there are two right here. Yep, so HCl, there are two. Perfect. Let's go ahead and plug that in. So 2 moles of HCl. And how many moles of lead chloride are there? How many moles of lead chloride are there right at the end? Again, if there's no number just means, yep, just means 1. Excellent. All right, and our last step, right? So we've gotten rid of moles of lead chloride. That's great. But now we need to get rid of moles of hydrochloric acid and finally get to our grams. So we're trying to get to our grams right here, the mass of hydrochloric acid. So we need one more step here, and then we're almost done. So multiply by this. All right, and our last step here comes from the molar mass. Remember, taking a look here, we said we need the molar mass of HCl. So here's our molar mass of HCl. It's 36.46 grams per mole. So I can write it as a fraction, 34.46 grams of HCl, all divided by 1 mole of HCl, or I can flip it. So we need to figure out which one should we use. So I can also do 1 mole of HCl divided by 36.46 grams of HCl. Okay, so I can use either of these. Let's figure out which one makes sense. So if I have moles of HCl in the top here, where does moles of HCl go in the next step? Where does moles of HCl go in the next step? As always, on the bottom. So moles of HCl goes on the bottom. So which fraction should I use here? Should I use the first one or the second one? Should I use the first one or the second one? In which of these two fractions is moles of HCl on the bottom? I see Annette, I see Ryan typing, I see Sylvia typing. Again, which of these two fractions has moles of HCl on the bottom? That is the question. Thank you, Sylvia. Need more participation? Again, I really do want to dismiss you, but I need answers. Yeah, the first one. Thank you. So we're going to go ahead and use the first one. Let me go ahead and just move this one over. Cool. So that being said, we have now gotten rid of moles of HCl and we're left with grams of HCl. Let's go ahead and multiply these together really quickly. On the top, we've got 65 times 1 times 2 times 36.46. In the chat box, what does that equal? Go ahead, grab your calculators and tell me what does that equal. What do I get on the top? What do I get on the top? Right, here's what I'm looking for. 65 times 1 times 2 times 36.46. What do we get? Thank you. I see Christine in the chat box. I see Annette typing. I see Sylvia. What do we get on the top when you multiply 65 times 1 times 2 times 36.46? What do we get on the top? Beautiful, Ayla. Yes, we should get 4,739.8. What do we get on the bottom? 1 times 2, 78.1 times 1 times 1. It's being multiplied by 1 a lot, so that should just equal what? Yep, should equal 278.1. Go ahead and do the final calculation. Remember, the fraction is the same as saying divided by. So 4,739.8 divided by 278.1 equals what? Thank you, Sylvia. Thank you, Christine. Natalie, awesome. I see Gabby typing. I see Kevin. Thank you, Kevin. I see Ryan typing. Annette working. Perfect. Yes, you should get 17.04. And tell me, what were the units that we ended up not canceling out? Remember, what were we solving for? What were we solving for? What units did we end with? What units did we not divide or cancel out? Yeah, exactly, Christine. So taking a look right here, you should have ended up with grams of HCl. So our units down here would be grams of HCl. Make sure you specify grams or moles. I know sometimes it's tempting to just say HCl, but you need to specify whether or not you're solving for grams or for moles. Great job, everybody. All right, let me go ahead and jump on over to our attendance. All right, these starting chemicals in a reaction, are those called the reactants or the products? Tell me in the chat box. The starting chemicals in a reaction, are those called the reactants or the products? Go ahead, let me know in the chat box, everybody. Excellent. I see Christine in the chat box. I need more participation. Get me those answers in the chat box. Starting chemicals in a reaction, are those the reactants or the products? Reactants or the products? Thank you, Natalie. Thank you, Ayla. I see everybody in there looking good. Get your answers in there. Cool, cool, cool. All right, go ahead and fill this out in today's attendance. There's the link to today's attendance, and you are correct. These are called the reactants. Thank you so much, everyone, and I will see you later. You have 1 minute to get your attendance done, and then I'll start logging people out. Have a wonderful day. Again, watch the video tomorrow for the exam, and then I'll see you again on Friday. Have a